Look at this simulation. A mechanical drone instantly calculates a path and flies cleanly through a dense field of obstacles without a single collision. To achieve that level of autonomy, we need the right environment. Our goal is to install, compile, and run the Fast Planner simulation so you can command a virtual drone through an unknown 3D space. Before writing any commands, verify your operating system. Fast Planner requires strict ROS compatibility. You need either Ubuntu 18.04 running ROS Melodic or Ubuntu 20.04 running ROS Noetic. Setting up this specific simulation environment gives us a sandbox. It bridges the gap between raw mathematical pathfinding algorithms and testable autonomous flight. Step 1 is acquiring the necessary dependencies. Open a new terminal window. The planner relies on a specific nonlinear optimization library called NLopt. You cannot use the default package manager for this. You must build version 2.7.1 directly from source. This terminal mockup shows the exact sequence required. Clone the NLopt repository, create a build directory, and execute the cmake and make install commands until you see the completion message. Next, install the Armadillo C++ linear algebra library. This one is straightforward. Just run the standard apt-get install lib-armadillo dev command. Without these two mathematical libraries properly installed, the planner's advanced B-spline trajectory optimization equations will fail to compile in the next step. Now that the system dependencies are resolved, we shift our focus to the local project workspace. Create a fresh Catkin workspace, navigate to its source folder, and clone the Fast Planner repository. Back in the root of your workspace, run the Catkin make command. This terminal screenshot shows the rapid compilation output you should expect, ending with a clear build target success message. Depending on your hardware, this process takes time. Let it run completely and verify the final build finishes without any fatal errors. Compiling the workspace translates the raw GitHub repository code into executable ROS nodes. These nodes need to be ready to communicate with one another to run the simulation. With the code built, we move from preparation to visualization. First, source the develop-setup.bash file. This is a critical step. Without it, your terminal will not recognize the ROS packages we just compiled. Launch the RViz visualizer by typing ROS launch plan manage rviz.launch. The interface will open, but it will initially appear entirely empty. Leave the first process running and open a second terminal tab. Inside it, source the environment setup file again. Now type ROS launch plan manage Kino replan.launch. The two isolated nodes link up and begin sharing data. Switch back to your RViz window. It immediately populates with a randomly generated 3D map, a dense set of obstacles, and your virtual drone model. Separating the visualizer from the planner logic prevents terminal clutter and ensures background nodes don't crash each other if one process hangs. Now we have an active, interactive simulation environment. This interface mockup shows the top toolbar in RViz. Focus on the button highlighted here, the 2D nav goal tool. Click that tool, then click any valid empty space across the map to set target coordinates. The system reacts immediately. The planner instantly creates a colorful trajectory line, and the virtual drone smoothly banks around blocky obstacles to execute the flight path. For a different approach, you can swap the launch command from Kino replan to toporeplan.launch. This runs a topological path searching algorithm, exploring multiple distinct routes through the full map to find the best option. By setting up and mastering this virtual workflow, you create a safe environment to test and validate these advanced flight algorithms before ever risking a physical quadrotor in the real world.